PMO 2022 National Stage problem number 8. For having next videos, subscribe, turn on the bell, like the videos, and if you wanted more explanations, send message through my WhatsApp number. Okay, the problem says the set S1 to 2022 is to be partitioned into n disjoint subsets S1, S2 to Sn such that for each I belongs to 1 to n, exactly one of the following statements is true. For all xy in Si, with x is not equal to y, GCD of x and y is greater than 1. For all xy belongs to Si with x is not equal to y, GCD of x and y equals 1. Find the smallest value of n for which this is possible. Okay, so at first I say an example. S1, A2 means AI means all multiples of I in S between 1 to 2022. So, because our set is 1 to 2022, so S1 is A2 means all even numbers from 1 to 22. S2 is A3. A3, I mean all multiples of 3. Okay, so here, so you should at first explain here that AI is what? AI is multiples of I between 1 to 2022. Okay, so A2, A3, 4, 5, 7, 11, 13, prime numbers 17, 19, 23, 29, 31, 37, 41, 43. And S15 is 1 and P, that P is prime, and P is at least 47, all prime numbers only. And okay, so these sets we want to prove. Let me tell you something. For example, 6 is in A2 and A3, but the problem says they are disjoint sets. So if you have if they have common elements, you can remove that element from all of them except one subset. And then we don't have any problem. For example, 6, if you remove 6 from A3, then still all the subsets are okay. Or for example 30 is in S3, S2, S1, so you can remove S30 from S3 and S2 and then you don't have problems. So you can see that if you find an example or anything that they are not disjoint by removing the elements that are in more than one subset, in all of them except one, again our subsets is okay. So the next one. We say we want to prove that if k is between 1 to 2022, it is in at least one of them. If k is prime, so it is 2 if it is 2 in S1, if 3 in here, if it is 43, it is in here, and if it is greater than 43 means at least 47, it is in S15. So for k prime is okay. Suppose k is not prime otherwise, so consider q is the smallest prime number that divides k, because k is not prime, and q is the smallest prime, so k is at least q squared. And we know that if q is less than 43, we consider all multiples of them. If q is greater than equal 47, means greater than 43, then k is at least 47 squared and a contradiction. So we found an example with 15. Now we want to prove that the answer is 15. So by that example, we can say our answer is less than or equal 15. Now we want to prove answer is at least 15. We prove it by contradiction. Assume on contrary that there is an example with less than 15 subsets. Okay. If all elements in a set is even, now I want to prove, let me tell you some general things. I want to at first say we have A2, that we have all multiples of 2, then we have all multiples of 3. My idea is this. Okay, so if we don't have A2, then let's see what we have. Then if we don't have A2 means in each subset we have at least one odd number, because if in a subset all of them are even, so you can add all the even numbers to that subset. So if in each subset we have at least one odd number, then consider these numbers: 2 times 47, 2 times 53, 2 times 109, prime numbers greater than equal 47. If you count them, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 numbers. I want to say all of them are in different subsets, because if two of them are in one set, Then without loss of generality, we can assume that 2 times 47 and 2 times 53 are in one subset. Then if we consider the odd number, because we said in each subset we have at least one odd number. This odd number, because these two have GCD2, so O1 and this number also must have GCD2 by the assumption of the problem, must have GCD greater than 1. Because it is odd, so O1 GCD of O1 and this number is 47, O1 and this number is 53, so 47 divides O1, 53 divides O1, so LCM of 47 and 53, which is 47 times 53 divides O1, so O1 is at least 47 times 53, which is greater than 2022, and that's a contradiction. So we've concluded that we have A2. Now let's consider, you can if you count them 1 to 15, you can use the same proof. Why? Because if you change all 2's to 3, then you can use the same proof. You say I have A21 also here, 15, 3 times 47 to 3 times 109. I have 14, 15 subset here, also A2, 16. For 3, 5, 7, 11, 13, 17, because 17 times 109 is also still less than 2022, let's not recall that. So we can say we have A2, we have A3, A5, A7, A11, A13, A17. Until here we have 7 subsets. Now I want to prove for 19. If you consider 19 times 47, 19 times 103 we have. Okay, until here 13 subsets, and also from 2 to 17 I have 7 subsets, A2 to A17, 7 plus 13, 20 subsets. Contradiction, because I want to check the case that our subsets, number of subsets is less than or equal 14, and we want to contradict that. Okay, so we have A19. Now if you consider for 23, the last one is 23 times 83, 9 here, and also until here 7, 1, 8 subsets, A2 to A19. Here 8 is for A2 to A19. I have 8 subsets, and 9 here, all of them different subsets, so 8 plus 9, 17. So also we have A23. For 29 until A23, I have 9 subsets. If you consider 29 times and the last one that is possible is times 67, so 5, 9 plus 5, 14. If you also consider 29, you can see that 29 cannot be in any of these 5 subsets, because if you consider 29 in any of them, 29 times 47, so GCD of 29 and that number is 29, and because the GCD is 29, so all the numbers in that subset must be multiple of 29. And we want to consider if we don't have 29, what happens. So if we don't have A29, if we don't have A29, then 9 plus 5 here plus 1, the subset that contains not 29, it is 15, and that's contradiction, so we have A29. If we don't have A31, I want to prove that we have A31. We have 10 plus 31 times 61, 1, 2, 3, 4. And also you consider 31, again 15 subsets. Contradiction, so we have A31. Now for 37, you consider until A2 to A2 to A31. To A31, we have 11 subsets, and if you consider 37 times 47, 37 times 53, we have 2 subsets here. You consider 37, 37 squared. We can prove easily if we don't have A37, all these things are in different, all these elements are in different subsets. And 2 here, because 37 times 47, 37 times 53. So 2 plus 1 plus 1, 4 plus 11, 15, again contradiction, and we have A37. For 41, you say until A2 to A37, we have 12 subsets, 47, 41 times 47, 41, 41 squared. If we don't have A41, all these 3 elements are in 3 different subsets. 3 plus 12 is 15. Contradiction, so we have A41. For 43, you say until A2 to A41, 13 subsets, 43 and 43 squared, 2 subsets. If you don't have A43, 15 subsets. So we have A43. So until here, A2 to A43, we have 14 subsets, And if our answer is less than 15, so we have only these 14 subsets. But as you can see, 47 is left contradiction. So our answer is at least 15 because we had an example that in that example answer was 15. In that example we had 15 subsets. So we can here say, because we proved by an example in the beginning of the proof that answer is less than or equal to 15. So we've proved that the answer is equal to 15.